The central processing unit, or CPU, is often referred to as the brain of the computer. It is characterized by its integration of circuits and the presence of multiple cores. Each core is designed to process instructions independently, thereby facilitating complex computations and enabling multitasking capabilities. Transistors play a pivotal role in computing technology, with billions of these tiny components integrated within a single CPU die. The organized arrangement of transistors creates a multi-layer structure that significantly enhances both processing speed and overall efficiency. In addition to the CPU, the motherboard acts as the principal circuit board that interconnects the various components within the computer system. It houses a chipset primarily responsible for coordinating the data flow between the CPU, memory modules, and peripheral devices. Equally important, the voltage regulator module, or VRM, is essential for supplying the appropriate voltage to the CPU. It ensures efficient power usage while maintaining optimal performance, typically operating with an efficiency ranging from 80 to 90%. Moreover, cooling systems are indispensable for managing the heat produced by CPUs, which can generate heat equivalent to the power consumption of approximately 16 LED bulbs. Advanced liquid cooling solutions are employed to maintain optimal thermal conditions. Power supplies play a crucial role in distributing stable electricity throughout the computer system. These units convert high voltages to the lower voltages required by various components, including solid-state drives, SSDs, and graphics processing units, GPUs. Focusing on the graphics processing unit, or GPU, it incorporates roughly 11.8 billion transistors organized into graphics processing clusters. This architectural design significantly enhances the computational power of the GPU, facilitating efficient parallel processing. The video further elaborates on the intricate manufacturing process of GPUs, which takes place in semiconductor fabrication plants. This discussion highlights the complexity and substantial costs associated with producing these advanced technological components. In contrast to CPUs, which are optimized for handling complex operations, GPUs leverage thousands of cores to execute basic arithmetic tasks. This design makes them particularly well-suited for applications demanding extensive parallel processing capabilities. Dynamic Random Access Memory, or DRAM, utilizes capacitors and transistors arranged in two-dimensional arrays to facilitate temporary data storage. This setup allows for incredibly rapid access times, measured in nanoseconds. However, DRAM does exhibit limitations in storage capacity when compared to solid-state drives. On the other hand, solid-state drives employ cutting-edge 3D NAND technology, which enables the storage of multiple terabytes of data. Although they operate at slower speeds than DRAM, SSDs provide a more permanent solution for data retention, offering significant advantages for long-term storage. Finally, traditional hard drives function utilizing rotating disks and read/write heads. While they offer a lower cost per terabyte, they tend to exhibit slower access times compared to both DRAM and SSDs, reflecting the trade-offs inherent in various data storage technologies.